This assessment asks us to tell whether the fluorination of an alkane is favorable or unfavorable, and then whether it is selective or non-selective. Let's start with the favorability first. We'll note here that we're going to break a secondary CH bond, a FF single bond. We're going to also form a secondary CF bond and the HF bond. We can use bond dissociation energies. So the secondary CH bond has a bond dissociation energy of 95 kilocalories per mole. I won't write the units just to save space. The FF single bond has a bond dissociation energy of 38, so it's a relatively weak bond. All told, we have to put in 95 and 38 to break these two bonds. That gives us a total of 133 kilocalories per mole of energy that are used to break those two bonds. How about the bonds we're forming? We're forming a secondary CF bond. That's going to be about 106 kilocalories per mole. So 106 kilocalories per mole are going to be released when this relatively strong CF bond is formed. Additionally, the HF bond, when it forms, is going to release 136 kilocalories per mole. So the HF bond is extremely strong. Summing those together, we get a total of 242 kilocalories per mole of energy that is released upon bond formation. We're putting in 133, we're getting out 242. This is an incredibly favorable reaction, having a delta H of negative 109 kilocalories per mole. I think I'm out of space. I am way out of space. I can fix that. There we go. Negative 109 kilocalories per mole. So a really favorable reaction. When we think about the selectivity, though, we really only care about the first step, meaning will the fluorine radical abstract the hydrogen to make a primary radical selectively or to make a secondary radical selectively? We know that the secondary radical is more stable, so it should form first. What this question is really asking is the first step endothermic or exothermic? Is it going to have a transition state that is reactant-like or product-like? So this is an application of the Hammond postulate. We can use bond dissociation energies to answer this question. So the primary CH bond that's breaking here, that is 98 kilocalories per mole. The bond that we're forming over here is 136. Delta H for this reaction is going to be 98 minus 136, or a total of negative 38 kilocalories per mole. So this is a highly exothermic first step to form a primary radical. As you might expect, this second step is also going to be highly exothermic, although slightly different, because now the secondary CH bond has a bond dissociation energy of 95. We'll use the same 136 over here. Doing that math, delta H is going to be equal to negative 41 kilocalories per mole. What does this tell us in terms of the selectivity of the reaction? It tells us that both of these first steps are very much downhill. So we can draw a reaction coordinate diagram to show them looking something like this. So maybe this is for primary. This would be for secondary. And the Hammond postulate tells us that a transition state, the transition state of an exothermic reaction, looks like the reactants. And so for that reason, there's not a big difference in energy between the transition state leading to primary and the transition state leading to secondary. The exothermic reaction is not selective.